Can you hear me? Okay. So 10 minutes left to start the lesson. In the meanwhile, I will pass you. I will pass in the chat 3 links to 3 data sets that we will. Okay, I will read the chat in a moment. So I'm copying in the chat 3 links, which are the links to Google Drive zip files, which are the 3 data sets that we will use today. So in the meanwhile, we are waiting for the lesson to start. You can start downloading them. Please download them in the order I will pass in the chat. So because we start with the first, and in the meanwhile, you can continue to download the rest. They are small data sets. It are just toy samples to play with during the exercises, but so you should not have difficulties to download them. Okay, so they are. Second. Yes. Send the project report and codes. Yes, it is not a problem. Don't worry. I will check your delivery, and I can see the submission as host, so not a problem. Okay. Just a test. If I write to the blackboard, can you see? I think yes, but no, yes. Someone no, someone yes. Okay, so I try to write. I don't know if I will use the blackboard, but if I will do it, I try to write it as bigger as I can. Are you trying the links? Can you download the data sets? Okay. No, it's not the same. It is a simplified version, which we have only one person, only one phase, and the class are binary. So we have the phase as the mask or not. So it's very simple. Could you please send the links? Yes. Yes. Second. So this view will not be in the record. Did you have a problem with the Blackboard last time?
Prof, I'm saying that when you share now, you share your PC probably, the screen of your PC. So that is the recording, and the camera is just a small, let's say, box that captures the the Blackboard. So if you want also to show in the recording what you write, you have to share between your PC and the room camera that captures the Blackboard.
Okay, thank you.
You're welcome.
But I think that I do not need the Blackboard, but I will see. Okay. Okay. In the meanwhile, you can take the notebook about the image classification. You can download it from the first website, because we will start from part of the code of that exercise. So it is the last, yeah, it is the last lesson, image classification. Okay. So until last time, we talked about images, and we we talked about implementing a neural network, which we started with a simple feed-forward neural network, and then we also saw how to implement a convolutional neural network. You should be able to implement and train your convolutional neural network since you did the homework, and so you should be very good at do it. And actually, until this point, we had an image, and we want to classify that image depending as one of a finite number finite set of classes. So, yes, sorry, I have to record. Thank you. So today we will change the things a little bit, and we will see how to implement and train a neural network to perform image segmentation, which is a new task that you should have seen during the theoretical lessons with I think with Professor Boracchi. And just to contextualize a little bit the problem, let me share. So this is, for example, the web page of the Pascal Visual Object Classes Challenge. And this is a common use dataset for image segmentation. You have different kind of classes in the image, so person, animal, vehicle, indoor, bottle, chair, dining table, and so on. And the task here is not to classify the entire image, but is to decide for each pixel in the image to which class that pixel belongs to. So here there is an example. Sorry, can you mute yourself? I think there's one with the mic. Maybe you? Okay, so here there is an example in which actually we can have two different types of segmentation. The first is the so-called semantic segmentation, in which we have a finite set of classes and we want to classify, we want to decide for each pixel which is the class the pixel belongs to, or a more difficult task is the so-called instance segmentation, in which we want to, for example, if in an image there are multiple persons, for example, we want to not only decide that the pixel inside a person is a person, but that person is different from another person. So we want to distinguish also the different object belonging to the same class. Today we will concentrate on the first kind of task, which is semantic segmentation. So we want to decide the class of the pixel and not the instance. And this will be also the task for your second homework. So let's approach the problem in, let's start with a simpler example, just to give an idea of a possible way to obtain some kind of segmentation. You should have seen the localization task with a global average pooling layer with Professor Boracchi. So you can you confirm that you saw that this kind of task during lesson, and you know what I mean? Okay. So what is global average pooling? How can I perform localization with that kind of layer? No one? Yes, so some way we will so is a way in which we can establish which kind of uh, which neurons we will activate for a specific class. So we can in some way localize the object by checking which region on my feature maps will activate for a specific class. So, for example, I will keep slides from Boratti. This one. Can you see the slide? Yeah. So actually, uh, what we have to do is to, instead of the last fully connected layer, we will put at the end of our encoding network uh, a global average pooling layer, which is for each neuron of this layer. For each feature map in input, we will take the average over the pixels. Thus, if we, for example, add our last fully connected layer for the classification, we can take for each of the output classes the corresponding input weights. These weights are the importance of a specific input feature map in the prediction of that class. So if I will take, for example, I want to inspect, given an image, which is the region in the input which activates for a specific class, I will keep the weights in input to the neuron corresponding to that class, and I will produce the weighted sum of my input feature maps. Then actually I have to resize the feature map to the original input side to obtain the localization at the original input scale. So let's start through this example, which is not actually a segmentation network, but I think that it will give a good example of what means segmenting an image. So let's start with the CNN classification notebook. So I will keep it in a moment. Okay, this is the notebook. I don't know if you remember it. So in this case, we use you see Merced land use for classifying images belonging to to a set of land use classes, and we will keep some parts of this notebook, and we will change a little bit to deal with global average pooling and to deal with the new data set. So let's start by importing the libraries, and for the one that are using Colab, to mount the drive folder. Okay, so then we can unzip the new dataset, which is the mask dataset one. So simply change the
Professor, excuse me, could you enlarge a little bit the font size?
Sorry, there are a lot of reverbs in the room. Can you write it in the chat? Large, okay, for sure. Is it okay? Okay, so instead of the use Merced, you have to change only the name of the dataset of the zip file, and then we can unzip the new dataset. Okay, then we can. Okay, let's inspect the dataset. So we have three folders: train, test, and val. And for example, in the training, we will have two subfolders, so we can use the flow from directory approach, and we have basically two classes. We have images of persons with mask, and images of persons without mask. So we have a binary classification 0, 1. Okay, then we can, for example, run the cell for data augmentation if we need it. And here we have to change the folder for the dataset. In my case, it is mask dataset. Then actually, the classes are taken in lexicographical order. So if I want, so actually it will be, for example, mask 0 and no mask 1. I find more natural to have the class switched. So in this case, I'm going to use the dictionary to decide the order of the classes. So for example, here it will become true, and I will have in this case with mask to be 1. No, actually, it will have to be a list. So I have without mask and second element is with mask. So it will be it will assign to the class without mask the 0 index, and to the class with mask the 1 index. Okay, then I have to change the folders because they are coded in a different way. So instead of training, it is train. Instead of validation, it is val. And instead of test, no, okay, test is test. Okay, so I have this number of images for the two classes in training. In validation, I have this number of images, and in test, I have this other number of images. And if I inspect the class indices, I will have the order of the classes is the one I decide. So I have the class 1 for the with mask category, and class 0, the label 0 to the class without mask. So I can run also the cell for the data set. And here I have to change the things a little bit for to perform to put the global average pooling at the end of the network. Okay, so in this part we have the features extraction that actually it is useful from now on to call encoder. And okay, just to show you, I can have also things like this. I can have a sequential under a sequential. So for example, I can create a sequential code encoder, and then here I can create the encoder. Okay, and finally, at the end of the for loop, I can add the entire encoder to the model. This is just to show you another way to put together the things. So okay, actually, let's take the I want the output of the classification of the I want the feature maps of the convolution. So I want to, for example, to discard the max pooling if I am at the last layer. So if I am at the last convolutional block, I'm not doing the max pooling. Instead, I put here, instead of the flatten, I'm going to put the global average pooling, which is under the Keras layers, and it's called global average pooling 2D. So 2D because for each channel of my input volume, I will performing the average of the values. Okay. And finally, I have to put the fully connected layer to perform the classification, and it is it has the number of classes as output. I don't remember if okay, here it is not 21, but the number of classes are 2. So here I have 2 output neurons. Okay, this is another way to do it, but We don't need them. Okay, so let's say the summary of the model. We should change dynamic classes. Yes, thanks. No question. Okay, better to use line classes. Yes. You can write the code as you prefer. Yes, it will be global. You don't see what is in the first sequential, but it just, you can write it just to show you another way. If you want, if you don't want to inspect the internal sequential, if you don't need it, you can put it in this way. Okay, so we can, for example, we can train with the categorical cross entropy. Actually, it is a binary classification, but we will have two output neurons, so we can use the categorical. We could use also, for example, a single neuron in general for the binary classification with a sigmoid, and in that case we can use the binary cross entropy as loss. But in this case, we will use the categorical since we have two output neurons. Then, for example, we can use the start TensorBoard, and then let me change just the directory for the experiments. Okay. But actually, I have to create the folder. I'm just deleting. Okay, and then we can call the fit. 21. Okay, the output of the dataset is, we have to change it to, I'm changing it manually. You can simply run also the cell with the variable. Okay, let me rerun. This one not needed. So new class is 2. It should be correct. Okay. Okay, it is training. It should be take few epochs to converge. It is a very simple task. Actually, the dataset is composed by images of simulated phase mask So they are very. It's very easy for the network to check whether the mask is on the face or not. Actually, they are all white masks, so it's very easy to learn a network to perform this kind of task of classification. So let's wait. Were you able to train the network too? So we're training it quite well. The training loss is decreasing, the validation loss is decreasing. Sometimes TensorBoard freeze. I don't know why. Okay. So let's stop here. It is quite good performance, I think. Okay. Now we can we have our network trained, and we can now, for example, use the network trained for classification to perform object localization. Let's see how. So let's take, for example, an image, which is I don't know, this one. No, I want an image with a mask. No. No. I have all images without mask. Incredible. Okay. So, for example, here I have an image of a person with a mask. As you can see, the masks are very. It's very easy to see that they are not so realistic. So it's very. We can simply check if there is a blob of white pixel, and then we can establish if there is a mask or not. So at this point, we can, for example, okay, let me clear all this stuff from the last time. Okay. So at this point, I can, for example, create a new model that we can call, for example, out model. In which we can take, okay, the inputs is the same of the last model input, but which we can take as output not only the prediction of our trained model, but also the activation of an intermediate layer. We can do it by, for example, okay, by listing all the output we want during the prediction. So we can say, for example, I want the model output, which is the prediction, but I want also the output from the last convolutional layer. So I can take, for example, model layers 0, which is the which is the encoder. And then I can take the output at a specific layer, for example, at -1. So I'm taking the last convolution. Inputs. And outputs, sorry. Okay. At this point, I can, for example, I have to localize the object in the original input space. So I have to resize my my features. We can do it with the a Keras layer, which is called Keras layers experimental preprocessing resizing. So under Keras layers experimental preprocessing resizing, I have a function which allows me to, given an input, to obtain a new volume with my with the spatial size I decide. So, for example, I want to resize to the volume to the original input space, which comprise 256 rows and 256 columns. And then I want to, for example, use bilinear as interpolation. This is the layer, and I can call this layer resize feature. And I will use later to resize the feature. At this point, I can produce the prediction given the output of my new model given this input image. So I can obtain the prediction and the encoder features by calling out model.predict of test image. Okay, I have to expand also. Okay, I have to add also the batch dimension. Okay, then I have to take the prediction, which is the argmax of the softmax over the second dimension, because the first is the batch one. Okay, so here I have the prediction, and we can check the prediction, for example. So the prediction is 1. So the network correctly identified that this guy has the mask on. Okay, at this point we can resize the features. So resize feature equal to resize to the function, and we can call the function too, and we can pass the last encoder feature. So let's shake, which is the shape. Now the shape are the input space as spatial dimension, and the number of channels that remain, the number of feature maps remains the same. So we have this new volume, which has the spatial dimension of the input. At this point, I can get, for example, the weights corresponding to the class, in this case, the mask class. So we can, for example, call a variable mask weights, and we can keep it as the last fully connected, are the last fully connected weights. So I can keep model layers -1, so I'm keeping the last layer, which is the fully connected layer for the classification. And then I can get the weights of this layer. And in particular, I have to keep the kernel, so it is 0 because the other is the bias. And okay, let's see which are the shape of these weights. So we have 128 values for the two classes, because each of the two output neurons have 128 values weights as input. I have to select only the one I'm interested in. So, for example, we can inspect the weights related to the mask. So I will keep the all the 128 weights corresponding only to the class mask. Okay, at this point, I have to perform the weighted sum of the input volumes with the mask weights to the class weights. And I'm going to do it in this way. So I'm changing the size of the resize feature, in the sense that I'm transforming the resize feature into a matrix. So I will flatten the pixels. So I resize my feature as 256 times 256 rows, and the number of channels remain the same. So in this case, I will have this dimension of for the matrix. Okay, so at this point, I can compute the class activation map using the linear algebra function matmul, which we can find under the TensorFlow library. And I will multiply the resize feature and the mask weights. But I have to expand the last dimension because I want a column vector. So mask weights will be 128 times 1. At the end, I will reshape the activation as an image. So I will have 256 times 256. Inside feature sensorize. Okay, without this. Wait. Okay. So we compute the class activation map. Let's visualize it. So to visualize the image, I will copy paste the code using Okay, so the argmax is needed to take the final prediction, because we have two neurons at the output. So we will have a probability distribution under two classes. So your output will be so the output of the softmax will be the probabilities for each class for the image to be one of each class, and then you have to keep with the argmax the index corresponding to the highest probability. Can you repeat what you're doing with resize feature? So we are resizing the feature because at the end of the encoder, since you perform subsampling with max pooling, actually you will end up at the end of the encoder with a lower spatial dimension with respect to your input image. What I'm doing is, before computing the weighted sum of my fully connected weights, I perform the weighted sum on the resize feature by upsampling the feature to the original input space. This is in this way you can visualize the localization in the original space. And the expand dims actually add a dimension to my input on the axis I decide, and this dimension has size 1. And actually I used here to add to transform the mask weight vector into a matrix. So I have added a second dimension, and here we use the expand dimension to the 0 axis that is the first, to add the batch dimension, which is 1 because we have only one image. Okay, for the model, instead, here I created a second model. Actually, I could create directly when we created the first model. Actually, I could okay, let me say in this way. So if we create a new model by giving the old model input and as output some layers of my old model, I'm creating a new model, but with the weights we trained before. But now my model at inference time allows me to get two outputs for the model, which are the model output and the feature map at the end of the encoder. So in this way, I'm saying to Keras, okay, I want a new model. The input is the same of the old one, and the output is R2, and are the prediction, which is the output of the old model, and the features of the encoder, which I can take from the old model with layers 0, which is the encoder, and from the encoder I get the -1s on the last convolutional layer. Yes, you can replace the resize with the reshape, the expand dimension, sorry. So at this point, sorry, I will pass the code from here so we can accelerate a little bit the things. Please check if you are able to copy past to see the code I share with you, okay? So it's just to visualize. Okay, as you can see, this method without training for object detection network or for segmentation network, is giving me, by only inspecting the activation in my feature map, is giving me a way to localize the object I'm interested in. Actually, as you can see, this is a very coarse localization, but for example, in the original paper, they used to take, for example, to segment the localization by keeping the by putting to one all the values of the class activation map that are above a certain threshold, and actually they used, for example, the 20% of the max of the class activation map. Okay, let me use the gray sample C map. Okay, in this case, 20% is low, so let's start with the 50%. Okay, so some way I can obtain a coarse segmentation from the class activation map, for example, applying a threshold, but this is a very coarse segmentation, but I think that is very useful because in this case, apart from the segmentation, this method allows you to understand actually what is happening in your network, and it is a good way to see which part of the image activates depending on a specific class after training, actually. Okay, so let's go to true segmentation. Okay, you had problem with the copy. Sorry. Okay, if you have problem, sorry, you can. Okay, it's okay. So let's go to a way to implement and train a network which is specialized for the segmentation problem. And let me go to the slides. Okay, so this is the typical convolutional network for classification. So we have the encoder and then the classifier, which is specifically designed for the task we are solving. Now, what if it's not actually you have already seen it during lesson, but the trick to perform image segmentation instead of image classification, one of the trick, because actually you see that you can, for example, train your classification network in a patch-based manner, and then you can slide, for example, the neural network around the image and classify the central pixel. But if we talk instead of convolutional neural network specialized for segmentation, they have a structure like this. So typically we have the encoder. The encoder is actually a network which is the same of the one used for classification. But we have also this part, the decoder, which in some way mirrors the encoder part, in which we are recovering the resolution as we go forward to the decoder. So typically, at the end of the encoder, we have sparse feature to the max pooling. What we need is a decoding network, which instead is upsampling the features, and then we can recover sharp features and sharper details by using in some way a structure that is the opposite of the encoder. So typically the decoder is composed by upsampling layer and convolutional layers. There are several ways in which we can do upsampling, and actually we have the convolution, the transpose convolution, which we can see as the opposite operation to the convolution. So it's often called deconvolution, and which allows to perform the upsampling, but also to learn the filter during the upsampling. And this is the advantage of using the transpose convolution. The other way, which is often used, is to perform first the upsampling with an interpolation algorithm. So, for example, it's very often used the bilinear upsampling, and then the upsampling is followed by a convolutional block. So these are the two options that are most used. So we can have transpose convolution, in which we learn the filters, and the upsampling is done for free. And on the other side, we can see the transpose convolution as the sum of an upsampling. So we can perform, for example, an upsampling with bilinear interpolation to the sides, to the shape we want, and then we can perform a convolution to recover the details from my upsampled features. Actually, this kind of approach has some limitation, because I can lose a lot of details during the encoding. It's like I'm compressing the information. So it could be difficult for the decoder to recover the details from the encoded representation. So what is typically a good approach, which turned out to be the winner approach, is this kind of structure, which is encoder decoder, but the key points of this kind of architecture are the skip connection. Skip connection allows me to connect features from the encoder to the corresponding features to the decoder. And that they are skip connected in the sense that we can, for example, here we can concatenate the feature from the encoder to the feature from the upsampling layer, and we can obtain a unique input volume to my decoding convolutions, or I can sum, for example, the features. And okay, so today we will start from an architecture which is very similar, is a simplified version of the unit. actually we will see a very simple encoder encoding decoding network, and we will apply this network. The first problem to which we will apply this kind of approach is on the second dataset. So can you can prepare for the second link, the second dataset I sent you at the beginning of the lesson, which is the segmentation dataset. It's called segmentation dataset. It is okay. It is a dataset, very simple actually. It is a dataset composed by aerial images, and what we want is to segment, so to recognize the buildings. So for each pixel, I want my network to predict if that pixel is belongs to the background or to the buildings, which is often called foreground. So when we have two classes, actually the one of the way to call the classes are background and foreground. So let's open a new notebook. I will share it in a moment. Okay, actually we can copy paste some part, for example, the first cell. The second one. We have to mount the drive folder again. Okay, so then you have to, for example, no, okay, the first thing we do is to unzip the dataset. So as usual, unzip content drive, my drive segmentation dataset for the one that I use in Colab. Otherwise, you have to unzip on your local machine. Okay, also in this case, I prepared, this is a very simplified version of the original dataset. So also in this case, I divided it into training and validation sets. And I'm going to show you a trick to use what we have learned until this point regarding the data loading and to adapt what we are what we learned from the last lectures to perform image segmentation. So actually we are going to create a data loader which will gives me as output the pair input image and the corresponding target, which is the same image but with 0 and 1s as values for the pixel, where 0 is corresponding to the background class and 1 to the foreground class. So let me, we can copy paste also the part for the generator. okay, with a little modification in the sense that I'm going to create two image data generator for the image and for the target mask. So this one will give me the data augmentation for the RGB image. This one will give me the mask corresponding to the first. So here I changed a little two things, which are the fill mode. Instead of constant, I put reflect, since I want to generate after the for example the transformation like rotation. I don't want zeros in the new pixels, but I want to reflect the image, and the same things to the mask. And obviously for the image data generator corresponding to the mask, I'm not dividing by 255 because they have not to be normalized. Same thing for the training image data generator and mask for the validation and test image and mask data generators. Actually, since the things changes a little bit, I can copy paste on code file. Okay, you will find it on code file on the same link we used before. Okay. At this point, I can, for example, use okay, I can create the data set. So let me, I don't know, let me copy it from here. Okay, so let's start from here. So we can have, and I can pass also this on code file. Okay, let me put some symbols to separate the cells. So here I'm creating the data set, the generator from using the flow from directory that we know. So I'm giving the training images folder, and class mode is none because I don't want to. I do not. I do not have classes. Shuffle through interpolation bilinear. Okay, now I have to create another generator. So I can call from mask data generator flow from directory. In this case, I have mask. Okay, and the things that is important in this case is this one. This is the most important thing. The seed. Here I have to set the seed because if I perform an augmentation, a transformation to the RGB image, I have to obtain the exact transformation also on the corresponding mask. Otherwise, for example, the RGB will rotate of 30 degrees, while the mask is only shifting, and they will not correspond when we will perform the training. Okay, so I have to do it for all the image, for all the subsets, sorry. So I can copy this. This valid. Valid. Okay, let's stop here. Don't care about the test set. Okay, so we found for the training 500 images, 500 corresponding 500 masks, and okay, this is the validation, sorry, and 100 images and 100 masks for the validation set. Okay, at this point, I can simply obtain the total generator, so the generator that gives me the pair image corresponding mask, by simply, okay, for example here, by simply calling the zip of the two generators. At this point, I will obtain a generator which keeps the outputs of the two generators, of the two separate generators, and it will put them in pairs. Same thing for the validation. So the valid gen is equal to zip valid gen valid mask gen. Okay, just to be sure that we will start from the same point, I'm going to copy the code on code 5. Okay. Okay, at this point, I can create the dataset as always. So I will have df.data.dataset.from generator, and the output of the mask. The mask is loaded from memory as an RGB. So I have to, in this case, one of the way of treat with this kind of data loading is, for example, to define a new map function in which we prepare the target. So we can define a function prepare target, which will take the couple image and target, and it will return the image as it is, while we want to convert the mask from, okay, let me write it down here. The mask now is has these dimensions. Where the channels are 0, 0, 0 RGB for the background, so black, and white, so 255, 255, 255 for the foreground. And I want from this encoding to have the target to be 256 times 256 times 1. I want to have only a single channel in which I have 0 for the background, 1 for the foreground. One of the ways to do it is to, for example, use TF where. So TF where my target y is equal to 255, put 1, otherwise 0. So I'm converting the 255 values to 1, and after that I have to discard the last dimension. Okay, there is a smarter way to do it, which is use TF reduce any. For example, write it down, then I will explain. Okay, this means that if there is at least one channel that is different from 0 from the RGB, I will put 1 in the final output, otherwise 0. In this case, I have not to clip the dimension because they will be directly the one I wanted. Okay, at this point, I can apply the map function to the trained dataset. And then I can call the repeat. Okay, now that we know how to do it, I will copy and I will pass this code into code file for you. While you are deleting the code from code file, okay, maybe I can avoid you to edit some way. No, cannot. Yes, it is read-only, but I cannot write. So let's try now. I'm sorry for people is doing this kind of stuff, but okay. Okay, after we create the dataset, we can start with the model. Actually, we can visualize the dataset just to show you how it is. So let me okay, try to copy paste this code. And dataset is not defined. Let me run this. Okay. Right. Sorry. Okay, so I have to forgot something that is okay. Sorry, we have to modify here the prepare target function, and we have to add to reduce any keep beams equal to true. Otherwise, I want to keep the number of dimensions. So I want to have one channel instead of three. But if I do not set keep dimension equal to true, Keras will discard the last dimension. So at this point, it should work. because I have to run the cell again. Okay. So if you run the cell, you can iterate over the samples. Okay. So you can see that. Okay, you cannot see I don't remember if the data augmentation is active, but you can see the augmentations because actually we are using the reflection. So the black part of the images that we saw last lectures will not appear here because we have reflection as fill mode. The same for the mask. Okay, now we can create the model. So,
Professor, I'm sorry, can you paste the right version in the code bin?
of the generator?
No, of this one last cell.
This one?
Yes.
Actually, it should be the same that is here, but okay, let's start with the model. So, for example, let's start with the sequential. And we split the implementation. So let's create first the encoder. So the encoder is the same that we use for classification. So let's imagine to loop on a variable which is called depth. For example, here I will put it 5 convolutional layers or in range. And as usual, for each convolutional block, I will alternate convolution. So going to be, for example, we can start with a number of filters, as usual, which could be, for example, 8. And filters equal to start f, kernel size equal to 3 times 3. Then I want stride 1. The padding is same. I don't want to change my input dimension. And just for summary purpose, I will set the input shape. So if I am to the first layer, I will set input shape to be 256 times 256 times 3. Otherwise, it is dynamic. Okay, after that, I will put the activation. And after the activation, I will define the max pooling with pool size equal to 2 times 2. Okay, so this is the encoder. I have to multiply the starting function for 2 at each iteration. This is the encoder, and in a typical encoder-decoder architecture, you will find that you will not end up with a max pooling, but usually you have also a bottleneck layer, which can be another convolution. So I can put the same another convolution with another ReLU. And now I have to start, given this embedded representation of my input, and this is my encoding, I have to reconstruct the input resolution. So I have to, in some way, through a deconvolutional network, I have to recover the details from my sparse features. And finally, in the last layer, I can perform the segmentation. We will see how to do it in a moment. But okay, here I can actually mirror the encoder. So I start to decrease the number of features. So at each layer, I will have the number of features. So actually, and I can start a loop again on my 5 convolutional layers. Since I'm mirroring the encoder, I'm using the same name of convolutional blocks. And I'm starting to alternate, in this case, upsampling. So I'm using the version with the upsampling 2D, which is under layers upsampling 2D. I want to double my input dimension, and actually I want to use bilinear interpolation, which is typically used in this case. And then after the upsampling, I can apply nonlinearity through a convolutional layer to transform the upsampled features to some dense features. And this is done by applying convolution, which is actually could be the same we use here, for example. And then, as usual, I have the final activation. Okay, this is the encoder. And here I have a classification layer, which is not a fully connected anymore. But I have a convolution 2D as well. But I'm using a convolution I'm going to use a convolution with a spatial dimension of one neuron. So I have a kernel which is 1 times 1 times my input channels. This equal to perform a fully connected layer for each pixel in the channel dimension. So I'm convolving a fully connected, it's like convolving a fully connected layer through the input volume. Thus, for each pixel, I can obtain an output prediction. So here I have, for example, I can copy these. I have to change the kernel filter size, sorry. Yes, actually, we can left also same, but it not change because I have a 1x1 filter with stride 1, so it's not important. And finally, I have my activation. And in this case, okay, we can, for example, use the activation right here. The activation could be sigmoid. So the output of my classification network, segmentation network, sorry, has the same dimension, and it is better to show you. Max pool should be with the uppercase. Sampling with the uppercase and layers. So let's see the summary. Okay, so this is my architecture. Until this point is actually like the network we use for classification. Here we start the coding. So from 8 by 8 input volume, I obtain through the upsampling 16 rows and 16 columns. Then I use the convolution to reduce the number of filters and so on. So I'm actually mirroring the encoder. The same I am upsampling until I reach the original input space. And for the final convolution, this is wrong because actually here I have to halve the features, and finally I have only one channel as output. Okay, now it's correct. So we are increasing the spatial dimension and we are decreasing the channel dimensions. And finally, I obtain, in my last layer, I obtain this volume with only one channel. So for each pixel, I will have a volume. I will have a single value. And that value is the output of a sigmoid function. That means that for each pixel, I have a probability from 0 to 1 that pixel is a background or foreground pixel. So I can copy past on code file also this. So you will have the model. Okay. And then I can, for example, use, okay, let's write it down from scratch. So I have to compile the model. So I have to decide which is the loss. In this case, I'm not solving for a multi-class classification or segmentation. So I will not have a softmax in the output, but I have a sigmoid, so, and 0, 1 classes. So I can use directly the binary cross entropy. I can define, as usual, the optimizer. So I can use, for example, Adam with a starting learning rate. And here I have to decide the validation metrics. Okay, now I'm introducing a new metric for segmentation, which is called intersection over union. Okay, let's see this image. Last times last time we have seen as validation metrics the accuracy, which is the frequency I'm correctly predicting the class for my images. But when the accuracy when dealing with image segmentation doesn't work very well, and the problem is it's very easy to see the problem in this image. For example, as you can see, we have a lot of background pixels. So, for example, in this case, a network which didn't learn anything will have, for example, a 70% of accuracy on this image, or 80%. I don't know. Supposing that the white part is the 20% of the image. So a network that learned to predict always the same 0 class, we will have a very high accuracy. So a good metric for evaluating a segmentation network is the so-called intersection over union. Let me find an image to show you. This is a very cool image. Okay, this one. So suppose that you have your prediction and the target mask. The intersection of a union is a measure of the percentage of that your prediction is overlapping on the target. So if your network correctly predict the class for the pixel, so if you have high performance, you expect your prediction to perfectly match the target. So you will have 100% of overlapping. Otherwise, if your prediction is incorrect, your overlap is it's between 0 and 100%, and you are not considering the background class here. So you are checking also only for the first class, and this makes this metric robust to the problem that is occurring with the accuracy. And this is actually simple to compute. We have to compute the area of overlap, so the part of where my prediction and the target is overlapping, divided by the total area given by the union between the prediction and the target. So let's write it down. To switch. Yeah. So let's define the metric intersection over union, which we have the correct mask and the prediction. And we have to compute the union and the intersection. So let me convert the prediction from a floating number between 0 and 1, because we have the sigmoid, to a binary mask. So I have y pred to be, for example, y pred greater equal of a certain threshold that is typically 0.5. So I'm going to put all the values above 0.5 to 1 and all the values below 0.5 to 0. So we can simply convert the Boolean mask I generate with this condition to a floating point. Okay. And then I can compute the intersection simply as the sum, and we can use reduced sum of the mask, the true mask, which is already in a binary form, and the prediction binarized. And this is the intersection. So I multiplied element-wise the two, and then I sum. I reduced to sum the results. So here I have the total number of pixels in the intersection, which is the area of the intersection. And then the union is given by the true positive, by the ones in the prediction. So all the pixels that are ones in the prediction. So let me write it this way. So we reduce to sum all the ones. So we are counting the ones in the target plus all the total sum of the ones in the prediction minus the intersection, and this gives me the union. After that, I can compute the intersection over union as the intersection divided by the union. Very simple. Actually, if you search, you will find that usually is added both to the numerator and to the denominator a small epsilon. And this is to avoid the division by 0. So if you are encountering an image which has where there are no classes, okay, you can avoid the division by 0 by putting a small epsilon in the division. And then I can simply add the metrics. For example, I want to compute both the accuracy and the intersection over union. And then I can add them into a list, and then I can compile the model as usual, and where set the loss, set the optimizer, and then I set the metrics. Okay, I will copy paste this on code file. Okay, we are almost there. Because now I have to, I'm simply copy pasting the cell the usual cell we use to fit the model. I'm only changing the experiment folder with another name, but is the same. And then, as you can see, I'm training the network. It is lower than we are used to see because we have a more complex network. And actually, I don't know if I'm using the GPU. No, I'm not using the GPU, but okay. It will be slower also with the GPU. But I can show you, for example, the result of a training. So after you train the network, okay, after you train the network, I mean, this is a not so good training. It's just an attempt I did on this configuration, and I reached. I don't remember. I reached 100 epochs with an Eiger, a 64% of intersection reunion on training, and 58% of intersection reunion on validation. And then you can use the same code we used before to check the data loading to show your results at inference. And these are the results. This is one of the results I obtained on a test image. And as you can see, the network is quite good to in some way localize the buildings, but it has no details in the output. This could be partially due to the fact that I simplified the dataset, so the dataset is very small, and probably it is not big enough to learn something that is very useful. If you are interested in this kind of dataset, you can find this dataset on the Kaggle competition of last year, and that should be on the course website. And you can have fun with the original dataset, which is bigger. Okay, so I think that we have no time to continue, but actually I want to show you very fast, but I will give you the notebook as well. Challenge is closed since we can download the dataset. Okay, so I will give you the dataset if you are interested. I will maybe I can upload on Drive or on OneDrive, and you can have the dataset. Okay, so I want to show you very last thing, which is multi-class segmentation. So now we have we work with binary classes. So we want to distinguish between background and foreground. But actually, the third data set I gave to you at the beginning of the lesson has multiple classes for each pixel. So it is the one from the BOK dataset. And actually, the principle is the same. In this notebook, you will find another way to create a dataset, which is by inheriting from the util sequence from Keras that allows you to create a dataset. It's very simple. I will comment the code as well, don't worry. But typically, you have to implement the init function in which you define, for example, the directory for the dataset and etc. You have to define which is the length of your dataset, so how many files you have in your dataset. And then you have to define the get item in which you can load the single image from memory. You can do all the preprocessing you want. In this case, for example, I manually transform the image, and then your dataset will output the pair, image, and mask. It is just another way to do it. Don't worry. The first method is enough, but if you want to have more control on your data loading, you can also build a custom dataset. And here you will find the details how to do it. Then you can put your custom dataset in from generator method from dataset, and from now on is equal to our data loading pipeline. Okay, as you can see here, we have different kind of images with different, for example, here I have segmented with red color the train, but we have cars, we have motorcycles, person, and etc. We have 21 classes. But what changed is a little change, is that you will have in the at the end of the coding part here, you will not have only one channel, but you have, when we perform multi-class classification, you will have the number of classes as the output channels for the final convolution. So you will have always a 1 times 1 filter for the output convolution, but you will have a number of channels that is equal to the number of classes, and then you apply the softmax as usual. Okay, in this specific example, I'm going to show you how you can, for example, take the encoder of BGG, for example, and then you have to write only the decoder. So this is sort of fine-tuning. So I can take, actually here I train it from scratch, but you can take the encoder of a BGG, and then you can attach your decoder to BGG. And finally, you have your final classification. So what changed in this notebook is the way I created the dataset. So I show you how to build a custom dataset. And then you have a multi-class problem. So the output of your final convolution has a number of channels equal to the number of classes. I try to comment the code as well as possible. Then, okay. This is an example of results. It's very bad because the network I trained is very bad. Also, in this case, I used a very simplified version of the dataset, so it could be not enough to learn something. Okay, so I think that we can close the class here. For what concern the the second competition, I think that you will receive a communication during the weekend as the last time, and the competition we will run for 2 weeks as the last one. You will have all the information through email. Okay. I think that's all. See you next time.